Look up. If the sky is clear tonight, if the window lets in even a pale suggestion of the night outside, you may see it. A light that is not a star too large, too steady, too close, too much a presence rather than a point. It has been there every night of your life, rising and setting with a rhythm that is older than any clock you have ever consulted, older than any calendar, older than the species that invented clocks and calendars. It has been there every night of your parents' lives and your grandparents' lives and every human life, all the way back to the first human lives, whenever and wherever those were. It has been there every night for 4.5 billion years, circling the earth in its slow, stately orbit, pulling the tides and lighting the darkness, and holding the planet's spin in its gravitational embrace. The moon. It is so familiar that it is easy to forget. It is extraordinary. Easy to forget that its presence is not a given, not a default, not a feature that comes automatically with planets. Most planets do not have moons like ours. Most planets do not have a moon at all, or have tiny, captured asteroids that provide almost none of the effects that our moon provides. The moon is anomalous. It is too large, relative to the Earth, for an ordinary moon. It formed in an extraordinary way, and its effects on the Earth, on its climate, its geology, its biology, and ultimately on the evolution of life and intelligence, are so profound and so pervasive that imagining a world without it is not merely a cosmological thought experiment. It is an act of imagining a completely different planet. Tonight, we are going to do exactly that. We are going to imagine the Earth without the moon, not the Earth as it is now. With the moon removed, that would be a different kind of catastrophe, a sudden withdrawal of the gravitational force that has been shaping Earth's behavior for billions of years. We are going to imagine the Earth as it would have been from the beginning if the moon had never formed, if the giant impact that created the moon had not occurred, if the Earth had continued, alone, in its orbit around the sun, without the companion that has shaped almost everything about the world we know. The world we will find is not the world we live in. It is stranger than that, faster, more violent, more extreme, more dark. A world that may or may not have produced life. A world that almost certainly would not have produced the kind of complex, stable, long-term conditions that allowed the evolution of intelligence. A world that is Earth in name and location, but almost nothing else. Let your breathing slow. Let the weight of the blanket settle. Let the familiar light of the moon, if it is visible tonight, if it is anywhere in the sky, remind you of how much you owe to something you have never once thought to be grateful for. And let us begin. The light above you, the moon tonight, wherever it is in its cycle, whether full and brilliant or a slim crescent, or entirely hidden on the far side of its orbit, is providing something to the night that we almost never consciously register. Light. Not the light of day, not the sharp, directional light of the sun, but a softer, reflected light. The sun's energy bounced off the moon's ancient, battered surface and traveling the 384,000 kilometers to Earth in just over a second. The full moon is bright enough to cast shadows. This seems unremarkable until you think about what it means. A rock in space, reflecting a small fraction of the sunlight that falls on it, is bright enough from 250,000 miles away to produce shadows on the Earth's surface. The human eye is sensitive enough to read by moonlight, though not comfortably. The human eye evolved, in part, in a world where moonlight was a resource, a precious source of illumination during the long nocturnal stretches of our ancestors' lives, when the ability to see, to move, to detect predators, to find food, was the difference between survival and death. Beyond the light, the moon provides something less visible but far more fundamental: stability. The Earth's axial tilt, the 23.5-degree angle between the Earth's rotational axis and the perpendicular to its orbital plane, is kept stable by the moon's gravitational influence. Without the moon, this tilt would not be fixed. It would wander. It would oscillate wildly over millions of years, between values as small as near zero and as large as perhaps 85 degrees. The consequences of this wandering tilt for climate and for life are so profound that we will spend an entire section exploring them. And beyond the stability, the moon provides the tides, the rhythmic rise and fall of the ocean surface, driven by the moon's gravitational pull on the Earth's oceans, is one of the most ancient rhythms of the living world. The tidal zone, the strip of coastline that is alternately submerged and exposed by the tides, is one of the most productive and ecologically significant environments on Earth. Life may have come ashore through the tidal zone. The tidal zone may have been the nursery of the terrestrial world. Without the moon, there is no tidal zone. Without the tidal zone, the history of life on land might have been entirely different, or might not have happened at all. These are the things we are giving up when we imagine a world without the moon: the light, the stability, the tides. And from these three things, so much else follows, so much that the world without the moon is not merely a darker, calmer, less rhythmic version of our world. It is a different planet entirely. How the moon was born, the violence that made beauty. To understand what a world without the moon would be like, we first need to understand how the moon came to exist, how this extraordinary, anomalous, enormous companion of ours was created. The moon was not always there. In the earliest days of the solar system, around 4.5 billion years ago, the Earth was a young planet, still in the process of growing by accretion, by the collision and merger of smaller bodies called planetesimals. The early solar system was a violent place, crowded with these planetesimals, with collision rates far higher than anything the solar system experiences today. The planets were growing through a process of continual impact and merger, building up their masses from the available material in their orbital zones. Approximately 4.5 billion years ago, perhaps 100 million years after the solar system first formed. Though the timing is uncertain and debated, a body approximately the size of Mars struck the young Earth. This body, called Theia by planetary scientists, after the Greek Titan, who was the mother of the moon goddess Selene, struck the Earth at a relatively low velocity and at an oblique angle. The impact was not a direct, head-on collision, but more like a glancing blow, though it was still enormously violent by any ordinary standard. The energy of the impact was immense. The collision melted and partially vaporized both Theia and the outer layers of the Earth. The material that was ejected from the collision, the vaporized and molten rock of both bodies, formed a disk around the surviving Earth, a disk of hot, glowing debris that orbited the young planet. Over the course of the next few thousand years, a brief span, even by geological standards, the material in this disk cooled and coagulated, pulled together by its own gravity, eventually forming the moon. The moon that formed from this disk was initially much closer to the Earth than it is today, perhaps only a few Earth radii away, rather than the 60 or so Earth radii of its current orbit. At this close distance, its gravitational influence on the Earth was far more powerful than today's, and the tides it raised were enormous, hundreds of meters high, perhaps, compared to the few meters of modern tides. But the tidal interaction between the Earth and the Moon, the same interaction that raises the tides, also gradually pushed the Moon further away, transferring angular momentum from the Earth's spin to the Moon's orbit. Over billions of years, this process has moved the Moon outward to its current orbit, and it continues today. The Moon moves about 3.8 centimeters further from the Earth each year. This is the story of the Moon's birth, a story of violence and heat, and the slow coalescence of debris into something beautiful and profound. And in the alternate world we are imagining tonight, this story does not happen. The impact does not occur. The debris disk does not form. The Moon does not coalesce. The Earth continues its orbit around the Sun, alone, without the companion that would have shaped almost everything about its subsequent history. What happens next? A world without the giant impact. In the alternate world, the world where Theia does not strike the Earth, the immediate consequences are not dramatic. The Earth continues to exist. It continues to orbit the Sun. Its surface continues to cool from the initial heat of formation. The oceans form, fed by volcanic outgassing and the impact of comets and water-rich asteroids from the outer solar system. The basic geochemical processes that characterize the early Earth, the differentiation of the core, the formation of the crust, the beginning of plate tectonics, all continue more or less as they do in our world. But there are differences, even in these early stages. The giant impact that formed the Moon also had important effects on the Earth itself, beyond simply creating the debris disk from which the Moon formed. The impact is believed to have contributed significantly to the final assembly of the Earth, adding mass, mixing the newly differentiated layers, and distributing the chemical composition of the Earth in ways that affected its subsequent geological evolution. Without the impact, the Earth might be slightly smaller, or slightly different in its chemical composition, or differently structured in its interior. More importantly, the impact dramatically affected the Earth's rotation. Before the Theia impact, the Earth was rotating at some rate we do not know exactly what, but it was likely slower than the extremely fast rotation that the Earth had immediately after the impact. The impact added enormous angular momentum to the Earth-Moon system, spinning the Earth up dramatically. In the immediate aftermath of the impact, the Earth was rotating very fast. A day was perhaps only 5 or 6 hours long. The subsequent tidal interaction with the Moon gradually slowed this rotation over billions of years to the current 2-4-hour day. Without the Moon, this tidal breaking never happens. The Earth's rotation, instead of being slowed by tidal friction, evolves only under the influence of the much weaker tidal forces from the Sun and the solar tides. While real, they are only about 46% as strong as the lunar tides in our world, and their effect on the Earth's rotation is correspondingly smaller. The result is a faster Earth. How fast? This is genuinely uncertain, because it depends on the initial rotation rate of the proto-Earth before the Theia impact, which we do not know precisely. But the Earth without the Moon might have a day that is 8 hours long, or 10 hours, or 12, something significantly shorter than our 24 hours, the residual of a rapid rotation that has never been fully braked. A faster spin changes everything. It changes the climate. It changes the atmospheric circulation. It changes the ocean currents. It changes the biological rhythms of every organism on the planet. A world spinning twice as fast as ours is not simply our world speeded up. It is a fundamentally different planet with different weather patterns, different temperature distributions, different biological opportunities and constraints. The Earth's spin, a planet running wild, an 8-hour day. Imagine it. Not in the sense of an 8-hour working day. Imagine actually experiencing an 8-hour rotation of the Earth. Dawn to dusk in 4 hours. Midday, 2 hours after sunrise. Darkness after only 4 hours of light, followed by 4 hours of darkness, and then dawn again. The rhythm of day and night, which is the most fundamental rhythm of life on Earth, running at 3 times its current speed. This faster rotation would have dramatic consequences for the Earth's atmosphere and its weather systems. The circulation of the atmosphere is driven by the differential heating of the Earth's surface. The tropics receive more sunlight than the poles, and this temperature difference drives the winds. But the rotation of the Earth modifies these winds through a phenomenon called the Coriolis effect. The rotation of the Earth deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere, producing the characteristic spiral patterns of storms and the bands of prevailing winds that organize the global atmospheric circulation. On a faster rotating Earth, the Coriolis effect would be stronger. The winds would be deflected more strongly. The atmospheric circulation would be more tightly organized into narrow bands running roughly parallel to the equator, rather than the broader, more meandering patterns we experience on Earth today. The weather systems, the mid-latitude cyclones and anticyclones that bring the variable, changeable weather of the temperate zones, would be smaller, more frequent, and more intense, because the stronger Coriolis effect would organize them into tighter spirals. The jet streams, the high-altitude rivers of fast-moving air that influence weather patterns across thousands of kilometers, would also be affected. In our world, the jet streams meander widely, producing the blocking patterns that bring prolonged heat waves and prolonged cold spells. On a faster rotating Earth, the jet streams would be more stable and less meandering, confined to narrower bands. This might produce more consistent, less variable weather in the mid-latitudes, but also a different distribution of rainfall and drought, with consequences for the pattern of life on the land surface. The tropical regions of the faster rotating Earth would be different from our tropics. The trade winds, the easterly winds that blow from the subtropics toward the equator in our world, organized by the Hadley cells of atmospheric circulation, would be stronger and more consistent on a faster rotating Earth. The tropical atmosphere would circulate more vigorously. The rainfall patterns of the tropics, the location and intensity of the intertropical convergence zone, the band of thunderstorms that circles the Earth near the equator, would be different. The ocean currents, which are driven partly by the winds, would also be different. The great ocean gyres, the circular currents that move warm water from the tropics toward the poles and cold water back, would be tighter and more constrained by the stronger Coriolis effect. The heat distribution between the tropics and the poles would be different. The poles of the faster rotating Earth might be colder, more efficiently cut off from the tropical warmth by the stronger atmospheric and oceanic barriers created by the faster rotation, and the day-night temperature cycle would be more extreme. With a day only 8 hours long, the night is only 4 hours of darkness. The ground cools during the night, but 4 hours is not long enough to cool as much as 16 hours would cool it. The daily temperatures swing. The difference between the temperature at noon and the temperature at midnight would be smaller on a faster rotating Earth than on ours. In some ways, this might be more benign for life. In other ways, the faster rhythm of warming and cooling would impose different biological constraints. The tilting world, seasons without a guardian. Of all the moon's influences on the earth, none is more fundamental to the history of life than its stabilization of the earth's axial tilt. This stabilization is subtle. The moon does not prevent the tilt from changing at all, but it constrains the rate and range of change to values that are compatible with long-term climate stability. Without this stabilization, the Earth's tilt would wander chaotically through a much larger range, producing climate variations of enormous amplitude over millions of years. The Earth's axial tilt, currently 23.5 degrees, determines the severity of the seasons. A larger tilt means more extreme seasons, hotter summers, colder winters, a larger temperature swing between the solstices. A smaller tilt means milder seasons, cooler summers, warmer winters, a smaller temperature swing. Near zero tilt means essentially no seasons at all, the same amount of sunlight in every latitude throughout the year. Very large tilt, approaching 90 degrees, means that the poles receive more sunlight annually than the equator, with half the year of continuous daylight and half of continuous night. In our world, the moon stabilizes the Earth's tilt in a range between approximately 22 and 24.5 degrees, varying on a 41,000-year cycle. This is a very narrow range, and it is one of the factors that has kept the Earth's climate relatively stable over geological time, or at least stable enough to allow the continuous evolution of complex life for the last 500 million years. Computer simulations of the Earth without the moon show that the Earth's axial tilt, without the moon's stabilizing influence, would wander chaotically, not randomly, but in complex, overlapping cycles driven by the gravitational influences of the other planets. The range of variation would be much larger, from near zero to perhaps 85 degrees, though the exact range depends on the initial conditions and the specific dynamical history of the system. The timescale of these variations would also be different. Large changes in tilt could occur on timescales of millions of years, which is slow by human standards, but fast by geological standards. What would this mean for the climate of the moonless Earth? When the tilt was small, close to zero, the Earth would have very weak seasons. The tropics would receive roughly the same amount of sunlight year-round, and the poles would receive very little sunlight in any season. The poles might be permanently cold and icy. The temperature gradient between the equator and the poles would be large, driving strong atmospheric circulation. The world might look something like an extremely glaciated version of our own, with large polar ice caps and a compressed habitable zone near the equator. When the tilt was large, approaching 85 degrees, the seasons would be extreme beyond anything in Earth's history. At 85 degrees of tilt, the poles would receive more solar energy annually than the equator. The summer at each pole would bring months of continuous, intense sunlight, with temperatures that might rival those of the modern tropics. The winter at each pole would bring months of complete darkness, with temperatures that might drop to hundreds of degrees below zero. The equatorial regions would have strange, complicated seasonal patterns as they moved in and out of the sun's direct illumination. The temperature swings over the course of a year would be larger than any temperature swings on the modern Earth. Between these extremes, the tilt would pass through intermediate values, each with its own climate signature. The Earth's climate, over millions of years, would cycle through states that range from a mildly glaciated near stability to a world of chaotic, violent, seasonal extremes, not in a regular, predictable pattern, but in the complex, sensitive to initial conditions manner of a chaotic, dynamical system. For life, this climate instability would be profoundly challenging. Complex organisms need stable conditions to evolve complex adaptations. The fine-tuned biochemistry of a warm-blooded animal, the precise flowering schedule of a flowering plant, the synchronized life cycles of predator and prey, all of these require a climate that is predictable enough to evolve for. A climate that changes dramatically on timescales of millions of years. The timescale on which species evolve is one that makes it very hard for complex adaptations to become established before the conditions that favor them disappear. This does not mean that life would not exist on the moonless Earth. Microbial life, with its short generation times and its biochemical flexibility, can adapt to almost any conditions. But complex, multicellular life, the kind of life that requires stable conditions over millions of generations to evolve its intricate ecological relationships, might struggle to establish itself in the chaotic climate of a moonless world. The history of complex life on Earth might have been very different, or might not have happened at all. The tides that never were stand on a beach. Feel the water rise around your feet. Notice how it comes in not all at once, but persistently, relentlessly, with a rhythm that you can predict to the minute if you know the time and the phase of the moon. This is one of the most ancient rhythms of the Earth's surface, and it is entirely the product of the moon's gravitational pull on the oceans. The tides are generated by the differential gravitational force of the moon across the diameter of the Earth. The side of the Earth facing the moon is pulled more strongly by the moon's gravity than the center of the Earth, and the center is pulled more strongly than the far side. This differential force, the tidal force, stretches the Earth slightly in the direction of the moon, and it stretches the ocean even more because water is fluid and can move. The result is two bulges of water, one on the side of the Earth facing the moon, one on the side facing away, and as the Earth rotates beneath these bulges, any given point on the coast experiences the passage of first one bulge and then the other, producing the characteristic pattern of 2 high tides and 2 low tides per day. The scale of the tides varies enormously around the world, depending on the shape of the ocean basin and the configuration of the coastline. In the open ocean, far from any coast, the tidal rise and fall is only about half a meter. In semi-enclosed basins, with the right resonant properties, the Bay of Fundy in Nova Scotia is the most extreme example. The tidal range can reach 16 meters, the height of a 4-story building. Most coastlines experience tidal ranges somewhere between these extremes, 1 to 3 meters in most places, 5 to 10 meters in the more extreme situations. The tidal zone, the strip of coastline between the highest high tide mark and the lowest low tide mark, is one of the most biologically rich and ecologically significant environments on Earth. It is exposed to air twice a day and submerged twice a day, which means it is home to organisms that must be able to tolerate both terrestrial and marine conditions. The selection pressure this imposes is intense, and it has produced some of the most remarkable adaptations in the biological world. Barnacles that seal themselves in their shells when exposed to air, mussels that cluster in dense aggregations to conserve moisture, intertidal fish that can breathe air through their skin when stranded in tide pools, sea stars that cling to rocks against the surge of the incoming tide. In a world without the moon, none of this exists. The tidal zone is gone. The coastline of the moonless Earth is a static boundary between land and sea, not dynamic, not rhythmically submerged and exposed, not the nursery of extraordinary adaptation and biological richness that the tidal zone represents in our world. There are still waves driven by wind, and there are still storm surges driven by atmospheric pressure systems. But the systematic, predictable, twice daily inundation that creates the tidal zone does not occur. The solar tides still exist. The sun also exerts a tidal force on the earth, though it is weaker than the lunar tidal force. Without the moon, the solar tides would be the only tides, producing a tidal range of roughly half the current neap tidal range, perhaps 20 to 30 centimeters in the open ocean, and perhaps a meter or two in the most extreme coastal geometries. This is a small but non-zero tidal range, and it would produce a very narrow intertidal zone, but it would not produce the rich, wide, ecologically significant tidal zone of our world. The loss of the tidal zone is not just a loss of habitat. It may be a loss of the very pathway by which life came ashore. The oceans of the moonless earth. The oceans of the moonless earth would be fundamentally different from the oceans we know, and not just because of the absence of tidal zones. The entire physical behavior of the ocean, its mixing, its circulation, its chemistry, its temperature distribution, would be altered by the absence of the lunar tidal forces. Tidal mixing is one of the most important physical processes in the ocean. As the tides flow over rough seafloor topography, over mid-ocean ridges, over the slopes of seamounts, over the complex terrain of the continental shelves, they generate turbulence. This turbulence mixes the water column, bringing cold, nutrient-rich deep water toward the surface and mixing warm, oxygen-rich surface water downward. Without this mixing, the ocean would be more strongly stratified, more sharply divided into warm, nutrient-poor surface water and cold, nutrient-rich deep water with a less permeable boundary between them. A more stratified ocean is a less productive ocean. The nutrients that accumulate in the deep ocean, the phosphorus and nitrogen that are essential for marine photosynthesis, would be less efficiently recycled back to the surface. The phytoplankton, which can only photosynthesize in the sunlit surface layer, would be starved of the nutrients they need. Marine productivity would fall. The food web built on phytoplankton would be diminished at every level. Less zooplankton, less fish, fewer marine mammals, less life. The thermohaline circulation, the great ocean conveyor belt that moves heat from the tropics to the poles and helps regulate the global climate, would also be affected. Tidal mixing contributes to the upwelling of cold water in the deep ocean that drives part of the thermohaline circulation. Without this mixing, the thermohaline circulation might be weaker, which would mean less efficient heat transport from the equator to the poles. The poles of the moonless Earth, already potentially colder due to the different atmospheric circulation of the faster rotating planet, would be even colder if the thermohaline circulation were weakened. The chemistry of the moonless ocean would also evolve differently. Tidal mixing affects the cycling of carbon dioxide between the ocean and the atmosphere. The turbulent surface, created by tidal currents, enhances the exchange of CO2 across the air-sea interface. Without tidal mixing, this exchange would be somewhat slower, affecting the ocean's role as a carbon sink and potentially affecting the long-term regulation of atmospheric CO2. The precise consequences for climate are complex and uncertain, but the absence of tidal mixing would remove one of the mechanisms by which the ocean buffers the Earth's climate. The seafloor itself would be different. Tidal currents move sediment, They carry fine particles across the continental shelves, sort them by size, deposit them in characteristic patterns. The rippled, wave-formed sediment structures that are so common in shallow marine rocks, the hummocky cross-stratification, and the symmetrical ripples of tidal environments would not form in the moonless world's oceans. The sediment on the continental shelves would be sorted differently, deposited differently, forming different geological structures. The seafloor of the moonless Earth, as preserved in the rock record, would tell a different story. The deep ocean basins of the moonless Earth would be quieter, not silent. There would still be thermohaline circulation, still internal waves driven by wind and by the interaction of currents with topography, still the slow creep of turbidity currents, carrying sediment down the continental slopes. But the powerful tidal currents that, in our world, scour the seafloor in shallow regions and drive internal waves in the deep ocean would not be present. The deep ocean of the moonless Earth would be more still, more stratified, more chemically stratified, with steeper gradients between the oxygen-rich surface and the oxygen-poor deep, the shorelines that would never have existed. The absence of tides would reshape the coastlines of the moonless Earth in ways that go beyond the loss of the tidal zone. Tides are geological agents as well as ecological ones. They erode rock, they transport sediment, they build and maintain the specific landforms that we associate with coastal environments. The great sea stacks of the world's coastlines, those dramatic pillars of rock standing offshore, detached from the main cliff by the relentless erosion of wave and tide, would be fewer and less dramatic. The tides accelerate coastal erosion in specific ways, concentrating it at the intertidal zone where the rock is repeatedly wetted and dried, expanded and contracted, attacked by biological organisms and by chemical dissolution. Without this tidal concentration of erosion, the cliff faces would erode more uniformly, producing less dramatic landforms. The estuaries, the partially enclosed coastal bodies of water where rivers meet the sea, would be different. In our world, tidal flushing is essential to the ecology of estuaries. It brings in salt water twice a day, carries out sediment, and maintains the oxygen levels of the water. Without tidal flushing, estuaries would tend to become brackish lakes, stagnant, stratified, poorly oxygenated, unable to support the rich fish and bird communities that real estuaries sustain. They would still exist wherever rivers meet the sea in sheltered bays, but they would be ecologically impoverished compared to our world's estuaries. The salt marshes and mangrove forests, the productive coastal wetlands that are among the most ecologically valuable ecosystems on Earth, depend on tidal inundation for their existence. These ecosystems develop in the upper intertidal zone, in the strip of coastal land that is flooded by seawater regularly but not continuously. The daily flooding and draining of the salt marsh creates the characteristic zonation of plant communities, from the low marsh dominated by cordgrass, which tolerates frequent flooding, to the high marsh dominated by more salt-tolerant upland plants, which is only occasionally flooded. Without tides, there is no intertidal zone, no rhythmic flooding and draining, no salt marsh, no mangrove forest. These ecosystems are not just beautiful, they are essential. Salt marshes and mangrove forests are the nurseries of many fish species, providing the shallow, warm, protected water that juvenile fish need to grow before they are large enough to enter the open ocean. They are carbon sinks, storing enormous quantities of organic carbon in their waterlogged soils, what scientists call blue carbon. one of the most efficient forms of carbon storage in the biosphere. They are storm buffers, absorbing the energy of waves and storm surges before they reach the terrestrial coast. Without tides, these ecosystems do not exist, and their loss would reverberate through the coastal and oceanic food webs in ways that are difficult to fully quantify. The beaches of the moonless world would also be different. In our world, beaches are dynamic systems, constantly exchanging sand between the beach face and the offshore bars in response to the tide cycle. The familiar rhythm of the beach, the smooth, gently sloping face of the wave wash zone, the berm above the high tide line, the tide pools in the rocky areas, is organized by the tidal cycle. Without tides, beaches would still exist wherever waves deposit sand on gentle slopes, but they would be more static, less dynamic, organized only by the seasonal variation in wave energy rather than by the daily tidal cycle. The coastline of the moonless Earth would be ecologically simpler, geologically calmer, biologically less diverse. The narrow band of life between the land and the sea would be narrower still, a mere line, rather than the broad, productive gradient that the tidal zone provides. And the consequences of this impoverishment would spread both inland and seaward, reducing the productivity and the biodiversity of the adjacent ecosystems. Life in a world without tides. The question of whether life would have evolved on the moonless Earth is one of the most profound questions we can ask about the role of the moon in Earth's history. It is a question without a certain answer, because the emergence of life is still not fully understood even in our world. But we can examine the ways in which the moon's absence might have affected the conditions for life, and from that examination, draw some tentative conclusions. The most fundamental conditions for life, liquid water, organic chemistry, an energy source, a stable chemical environment, are not directly provided by the moon. Water would exist on the moonless Earth, delivered by comets and asteroids in the same way as in our world. Organic chemistry would proceed in the moonless ocean as it does in our world's ocean. The sun would provide energy. These basics are not moon dependent, but the moon may have played an important role in the origin of life, or in the early conditions that life needed to get started. The tidal pools, the small, enclosed bodies of water in the intertidal zone, repeatedly filled and drained by the tides, have been proposed by some researchers as the ideal environment for the origin of life. A tidal pool that is filled with seawater at high tide and then left to evaporate during low tide concentrates organic molecules. Concentration is essential for the chemical reactions that led to life, because many of the key reactions, the polymerization of RNA or protein precursors, for example, require high concentrations of the reacting molecules. Without tides, there are no tidal pools. Without tidal pools, one of the proposed cradles of life is absent. This does not mean life could not have originated without tidal pools. There are other proposed sites for the origin of life: deep-sea hydrothermal vents, freshwater ponds with wet-dry cycles driven by rainfall, mineral surfaces in the shallow ocean. Any of these might have served as the origin site in the moonless world. But the probability of life arising might have been lower, and the process might have taken longer if the tidal pool pathway was unavailable. Once life arose, if life arose, its subsequent evolution would have been shaped by the absence of the tidal zone. In our world, the intertidal zone is one of the most intensively studied evolutionary laboratories. The extreme conditions of the tidal zone, the repeated desiccation, the temperature swings, the salinity changes, have driven the evolution of extraordinary physiological and behavioral adaptations. And some researchers argue that the intertidal zone was the primary route by which life colonized the land, with intertidal organisms gradually evolving greater tolerance for aerial conditions over millions of years. Without the tidal zone, the colonization of the land would have to proceed differently. Life would still have had some incentive to colonize the land the terrestrial environment offers. Sunlight and nutrients not available in the ocean, and there would be selection pressure for any organism that could exploit them. But the gradual, stepped transition from marine to intertidal to terrestrial that the tidal zone provides would be absent. The transition would have to occur in a single, larger jump from the subtidal to the fully terrestrial without the intermediate stepping stone. This harder transition might have delayed the colonization of land, or it might have prevented certain groups from making the transition at all. The evolution of amphibians from lobe-finned fish, the pivotal transition that brought vertebrates to the land, is thought to have occurred in shallow, coastal environments, possibly intertidal or near intertidal. Without the tidal zone, would this transition have occurred? Would vertebrates have come ashore at all? Or would the land have been colonized only by invertebrates and plants, without the fish ancestors that became amphibians and reptiles and dinosaurs and mammals? These questions do not have certain answers, but they illustrate the depth of the uncertainty about the biological world of the moonless Earth. The absence of the tidal zone is not merely an ecological loss. It may be the loss of the very mechanism by which the living world expanded from the ocean to the land. The first creatures and the missing shore. In our world, the first complex animals appeared in the sea, in the Ediacaran and Cambrian. They were marine creatures, soft-bodied fronds and discs in the Ediacaran, armored, hard-bodied, diverse animals in the Cambrian explosion. Their evolution was driven by the conditions of the shallow seas, the chemistry of the Ediacaran and Cambrian oceans, the availability of oxygen, the development of predation, the interactions of organisms with the seafloor sediment. In the moonless world, the shallow seas would exist, but their ecology would be different. The absence of tidal currents would mean that the shallow seas were more stratified, less mixed, with less nutrient upwelling from the deep. The chemistry of the shallow seas would be subtly different, perhaps lower in certain nutrients, perhaps differently oxygenated at different depths. These differences might have been enough to delay or alter the Cambrian explosion, or they might have been insufficient to prevent it. We cannot be certain. What is more certain is that the evolution of the specific lineages that led to land animals might have been different. In our world, the Devonians saw the evolution of the tetrapods, the four-limbed vertebrates from lobe-finned fish ancestors. This transition occurred in the late Devonian, approximately 375 million years ago, in environments that may have included tidal and intertidal zones along the coast of the ancient continents. The tidal zone may have been the ecological context in which the advantages of having limbs, of being able to move across the substrate and out of the water temporarily, were first selected for. Without the tidal zone, the selection pressure for limbed locomotion in shallow water might have been different. Fish would still have explored the margins of ponds and rivers and shallow coastal environments. The terrestrial environment still offers resources worth exploiting, but the specific ecological context of the tidal zone, the regular, predictable exposure of the substrate, the selection for organisms that could function both in and out of water, would be absent. The first land animals of the moonless Earth might have been different from our world's first land animals. Invertebrates, insects, and arachnids and myriapods might still have colonized the land, driven by the availability of terrestrial plant material and the absence of terrestrial predators. But the vertebrate colonization of the land might have been delayed, or proceeded differently, or produced different lineages. The specific biological world of the moonless Earth's land surface is almost entirely unpredictable from first principles. But it might have been a world without large vertebrate land animals, or a world where the vertebrate land animals were very different from any we know, or a world where the colonization of the land happened much later, giving the marine world much more time to diversify before its organisms began to venture ashore. The night that would have been total. If you have ever been in a place truly far from city lights in a desert, or a mountain wilderness, or on the open ocean, you know how dark a moonless night can be. Not merely dimmer than a lit night, but of an entirely different quality of darkness. A darkness that has depth, that is not the mere absence of light, but a positive presence, a thick and palpable thing that fills the spaces between the stars and makes the stars themselves seem very far away. This is a moonless night, and in the moonless Earth, every night would be like this. The full moon in our world provides approximately 0.001 lux of illumination, about 1,000 times less than daylight, but enough to see by, enough to navigate by, enough to read by in good conditions. The absence of this illumination, night after night, year after year, throughout the entire history of the moonless Earth, would have profound consequences for the nocturnal world. Nocturnal animals rely on the moon. Not all of them, and not in all ways. Some nocturnal animals actively avoid moonlit periods, hunting only on the darkest nights to avoid being seen by predators. But many nocturnal animals use moonlight for navigation, for prey detection, for orientation. The dung beetles of the Kalahari, for example, navigate by the polarization pattern of the Milky Way, which is only visible in the absence of moonlight. So in some sense they navigate by the moon's absence rather than its presence. But they navigate, and navigation of any kind requires a structured sky. The insects of our world have complex responses to moonlight. Many moths and beetles and other flying insects use the moon for navigation, maintaining a fixed angle relative to the lunar light as they fly, a strategy called light compass orientation that works because the moon is distant enough that the angle to it changes very slowly as the insect moves. In the moonless world, this navigation strategy would be unavailable for lunar light. Insects might navigate by stars instead, some already do, or by magnetic fields, or by other environmental cues. But the specific behavioral ecology of nocturnal insects would be different. The predators that hunt by moonlight, the owls and the cats, and the foxes and the weasels, would also be affected. Owls, in particular, are adapted to hunt in very low light conditions, their eyes and ears extraordinary instruments of nocturnal detection. But even owls hunt more successfully on brighter nights, when the contrast between prey and background is greater. In the permanent, lunar-free darkness of the moonless Earth's nights, the visual predators of our world would be at a disadvantage, and the arms race between nocturnal predators and their prey would have taken different evolutionary directions. The sea would also be different at night. Many marine organisms perform a daily vertical migration, ascending to the surface at night to feed on the phytoplankton-rich surface layer, then descending to the deep ocean during the day to avoid visual predators. This vertical migration is one of the largest daily movements of biomass on Earth. Billions of organisms, every night, moving up and down through hundreds of meters of water. The timing and extent of this migration is influenced by light levels at the surface, including moonlight. bright, full moon nights, the migration is suppressed, the organisms stay deep to avoid being seen. In the moonless world, the permanent darkness of the ocean surface at night might alter this migration in ways that affect the entire marine food web, the stars in an unlit sky. But the moonless night, for all its darkness, would not be featureless. There would be stars, not stars as most people living in the modern world experience them, not the handful of bright stars visible from a city, competing with the orange glow of streetlights, stars as they were before artificial light, stars as they appear in truly dark places, 10,000 of them, visible to the naked eye, arranged in the patterns that our ancestors mapped and named and told stories about. And in the moonless world, where there has never been a moon to brighten the night sky even slightly, the stars would be even more prominent, not brighter, but more consistently visible, because the moon's brightness can wash out dimmer stars when it is near full. The Milky Way would be spectacular, arching across the moonless sky, the plane of the galaxy visible as a complex, structured band of light, not the faint suggestion of it that modern city dwellers occasionally glimpse, but a vivid, detailed, unmistakable river of stars, with dark nebulae and bright star clusters, and the dim smudges of neighboring galaxies visible within it. On a clear night in the moonless world, the Milky Way would cast a shadow barely perceptible, but there, if you held a piece of paper at the right angle to the most brilliant part of the galactic center, the planets would be brighter in the moonless sky, not because the planets themselves would be different, but because they would not be competing with the moon's light. Venus, the brightest planet, already casts shadows in our world on very dark nights in the moonless world. This effect would be more commonly noticed. Jupiter and Mars and Saturn would be vivid presences in the night sky, their colors perceptible to the naked eye on good nights, and the sky would be darker between the stars. The airglow, the faint luminescence of the upper atmosphere produced by chemical reactions driven by the sun's ultraviolet radiation, would be more visible, a ghostly background illumination that gives the dark sky a faint, greenish shimmer. Meteorites burning up in the atmosphere, the shooting stars that we see most spectacularly during meteor showers, would be brighter and more spectacular against the darker background sky. The moonless night sky would be the most beautiful sky any eye has ever seen, assuming that eyes evolved to see it, which in the moonless world is itself uncertain. It would be a sky full of information. The positions of the stars, the movements of the planets, the structure of the galaxy, the rotation of the celestial sphere as the Earth turned. Any intelligence that evolved in the moonless world, with this magnificent, information-rich sky above it every night, would be profoundly aware of the cosmos, not because it is sophisticated, but because the cosmos, without the moon's washing glare, would be simply, immediately, obviously present. The atmosphere of a moonless world. The Earth's atmosphere would be different in the moonless world, though the differences are subtle and their consequences are large. The moon's gravitational influence on the Earth's atmosphere is real, though small. The same tidal force that raises the ocean tides also raises atmospheric tides. The atmosphere bulges slightly toward the moon, producing a global tidal pattern in the air. These atmospheric tides are weak compared to the oceanic tides, but they have measurable effects on atmospheric pressure and on the timing of rainfall. Without the moon, the atmospheric tides would be reduced to only the solar component, which exists but is less powerful. More importantly, the moon's role in stabilizing the Earth's axial tilt has implications for the atmosphere. With a stable tilt of 23.5 degrees, The Earth's atmosphere experiences the same seasonal pattern year after year, the same sequence of summer and winter, the same migration of the intertropical convergence zone, the same cycle of monsoons and dry seasons. This consistency has allowed the Earth's atmospheric circulation to evolve into a stable, organized system with recognizable, predictable patterns. With a chaotically varying tilt, the atmosphere of the moonless Earth would not have this consistency. The seasonal patterns would change as the tilt changed over millions of years. The atmospheric circulation would reorganize in response to the changing distribution of solar heating. The zones of rainfall and drought would shift. The jet streams would move. The monsoonal systems would strengthen and weaken. The Earth's climate zones, the tropical, subtropical, temperate, and polar zones that organize the distribution of vegetation and animal life, would not be stable features of the landscape, but shifting, transient patterns that changed on timescales of millions of years. The atmosphere of the moonless Earth would also be affected by the faster rotation. A faster rotating atmosphere is more turbulent. The stronger Coriolis effect produces stronger wind shear, and stronger wind shear promotes the breakdown of organized flow into turbulence. The atmosphere of the moonless Earth might be more turbulent, more energetic, with more intense and more frequent storms than the atmosphere of our world. Not necessarily larger storms. The size of storms is constrained by the scale of the atmospheric circulation patterns, which would be smaller on a faster rotating Earth, but more energetic, more violent within their smaller scales. The oxygen content of the moonless atmosphere is uncertain and depends on whether complex, photosynthetic life evolved in the moonless world. In our world, the current oxygen level, 21%, is the product of billions of years of photosynthesis by marine algae and terrestrial plants. If the moonless world had less marine biological productivity due to the stratified, nutrient-poor ocean and less terrestrial vegetation due to the climate instability and the potentially delayed colonization of land, then the oxygen level of the moonless atmosphere might be lower than 21%. A lower oxygen level would affect the physiology of any complex organisms that did evolve, and it would reduce the frequency and intensity of wildfires, the magnetic field, and the spin connection. The Earth's magnetic field, the invisible shield that deflects the solar wind and protects the atmosphere from being stripped away by the stream of charged particles that the sun constantly emits, is generated in the Earth's liquid outer core by the convective motion of molten iron. This convective motion is driven by the heat of the core and by the Coriolis effect of the Earth's rotation. A faster rotating Earth might have a different magnetic field. The Coriolis effect plays a role in organizing the convective flows in the outer core into the large-scale patterns that generate the dipolar magnetic field we observe. On a faster rotating Earth, the Coriolis effect in the core would be stronger, and this might affect the structure of the magnetic field. The field might be stronger, or it might be more complex with more multipolar components, more frequent reversals, more variable intensity. The details are genuinely uncertain and depend on the complex dynamics of the Earth's interior, but the magnetic field matters enormously for life on the surface. The solar wind, the constant stream of charged particles flowing outward from the sun, would, without the magnetic field's protection, gradually erode the Earth's atmosphere, stripping away the lighter gases and over time reducing the atmospheric pressure. Mars, which has lost most of its magnetic field, has a very thin atmosphere, partly because the solar wind has stripped away much of the original Martian atmosphere over billions of years. Venus, which also lacks a significant magnetic field, has a dense atmosphere, but Venus is much closer to the Sun than Earth and has a very different geological history. If the moonless Earth had a significantly different magnetic field, weaker or more variable, the long-term evolution of its atmosphere might have been different. A weaker magnetic field would allow more solar wind erosion, potentially reducing the atmospheric pressure over billions of years. A more variable field, with more frequent reversals and periods of weakness, might have exposed the surface to higher levels of cosmic rays and solar energetic particles during the periods of weak field, with potential consequences for the mutation rates of surface organisms and the distribution of ultraviolet radiation reaching the surface during atmospheric erosion events. The connections between the moon's absence, the Earth's faster rotation, the magnetic field's character, and the long-term evolution of the atmosphere form a chain of consequences that is difficult to trace with certainty, but the chain is real, and it suggests that even the geophysical evolution of the moonless Earth might have been significantly different from our world, in ways that affected the habitability of the surface over geological time. The calendar that could not have been. In our world, the moon gave us the calendar, not the solar calendar that most modern societies use, the 365-day year organized around the Earth's orbit of the Sun, but the older, deeper, more primitive calendar that every human culture has used at some point in its history, the lunar calendar, the organization of time around the cycles of the moon. The moon cycles through its phases from new moon to full moon and back to new moon in approximately 29.5 days. This period, the synodic month, is the basis of the month in almost every calendar tradition on Earth. The very word month is cognate with moon in English and in most other Indo-European languages, a linguistic reminder of the deepest roots of human time reckoning. The lunar calendar was not merely convenient, it was a profound cognitive tool. The moon's phases are visible, predictable, and regular in a way that almost nothing else in the natural world is. The return of the full moon is a date that anyone can determine with no instruments, no calculation, just a memory of when the moon was last full and a count of the days since. The lunar calendar was the first calendar available to any human with eyes and a memory, requiring no sophisticated technology or astronomical knowledge beyond what any careful observer would accumulate naturally. In the moonless world, this calendar does not exist. Time must be measured differently. The sun provides some time marking sunrise and sunset, noon, the annual cycle of the solstices and equinoxes. But the intermediate unit, the month, the unit between a day and a year, would not be provided by any obvious astronomical phenomenon in the moonless sky. This might seem like a small loss, but the lunar calendar was not just a practical tool. It was a cognitive scaffolding for the development of abstract thought about time, the ability to plan for events weeks in the future, to know that the full moon will come again in 15 days, that the spring floods will arrive in 2 lunar months, that the migration of the animals will begin at the new moon after the next full moon, was an early and important step in the development of the kind of long-range planning that characterizes complex civilization. The development of writing in our world is closely connected to the development of record-keeping, and record-keeping is most easily done when there are regular, memorable, clearly defined units of time to record. The lunar month was perhaps the first such unit. In the moonless world, the development of a complex calendrical system, and with it, the development of writing and record-keeping, might have been delayed or might have taken different forms. Navigation across a dark sea. In our world, the moon has been one of the most important navigational tools available to seafarers for as long as human beings have gone to sea. The moon's position in the sky, its altitude, its azimuth, its phase, provides information about the observer's location and the time of night. The precise timing of the moon's position relative to the stars was, in the era before GPS and electronic navigation, one of the primary methods of determining longitude at sea. The method of lunar distances, measuring the angular distance between the moon and a nearby star, and comparing it to a table of predicted positions, was the practical solution to the problem of longitude that dominated navigation for the better part of a century before the invention of the accurate marine chronometer. It required a sextant, a nautical almanac, and considerable mathematical skill, but it worked. It allowed navigators in the 18th century to determine their longitude to within a degree or so, enough for practical navigation across the open ocean. In the moonless world, this method would not exist. Navigation by the stars alone is possible. The stars give latitude through the altitude of the pole star or the transit altitude of other stars, and give local time through the rotation of the celestial sphere. But longitude determination without the moon, before the advent of chronometers and radio, would have been much harder. The stars themselves move in predictable patterns, but the patterns are subtle and require either a very accurate clock or a very precise observational method to use for longitude. The practical consequence is that open ocean navigation, the kind of navigation that allowed human beings to cross the Pacific Ocean and colonize every island, or to discover and settle the Americas from Europe, or to establish the global trade networks that drove the development of modern civilization, might have been delayed or might have taken different forms in the moonless world. Without the lunar navigation methods that made open ocean voyaging practical, the spread of human populations across the globe might have been slower, more limited, more coastal. This is, of course, a speculation built on the assumption that intelligent, seafaring humans exist in the moonless world, an assumption that, as we have explored, is itself deeply uncertain. But if we allow that assumption, the absence of the moon as a navigational tool would have shaped the history of human exploration and the patterns of human settlement in significant ways. Mythology without the moon. The moon is woven into the mythological fabric of every human culture that has ever existed. There is not a single human culture anywhere in the world that has not looked at the moon and made stories about it. The moon is a god, a goddess, a rabbit, a hare, a woman, a man, a trickster, a lover, a timekeeper, a ruler of the waters, a guide of the dead. The moon is Selene and Artemis and Hecate and Luna and Soma and Chandra and Thoth and Khonsu and Chang'e and Tsukuyomi. Why? Because the moon is the most dramatic, most variable, most personally meaningful object in the night sky. The stars are beautiful but remote. They do not change from night to night. They do not interact with the world below in obvious ways. The sun is too bright to look at and too constant to engage with directly. But the moon changes every night. It grows and shrinks and disappears and returns. It is sometimes a blade of light and sometimes a full, brilliant disk. It rises and sets at different times on different nights. It interacts with the world below it, moves the tides. It lights the darkness. It marks the months. It is personal in a way the stars are not. In the moonless world, human mythology, if human mythology existed, would be built around different objects. The stars would certainly be mythologized. The planets, with their slow, complex movements against the background of the stars, would be objects of mythology and astronomy. The sun, the supreme light giver, would be the central astronomical deity, but the moon's specific role, the cycling, changing, personal, tide-moving, night-lighting presence would be absent. The mythological systems built without the moon would be different in structure as well as content. The moon provides a natural metaphor for cyclical time, for the processes of growth, fullness, decline, and renewal that characterize so many aspects of the natural and human world. The agricultural cycle, the human menstrual cycle, the cycle of the seasons, all have been mapped in human mythology onto the cycle of the moon. Without the moon, the natural metaphors for cyclical process would come from different sources: the seasons, the tides of rivers, the annual migrations of animals. The resulting mythology would be organized differently, would use different metaphors, would tell different stories about the relationship between human life and cosmic time, the human mind and the lunar rhythm. There is evidence, disputed but real, that the human body has evolved rhythms that are synchronized with the lunar cycle. The human menstrual cycle averages approximately 29.5 days, the same length as the lunar month, a coincidence that may or may not be coincidence. The sleep cycles of human beings show some correlation with the lunar phase, with studies finding that sleep is slightly shorter and starts slightly later around the full moon. Some marine organisms synchronize their reproduction with the lunar cycle, and some researchers have proposed that human biological rhythms might retain traces of ancient lunar synchronization from the deep evolutionary past. Whether or not these specific correlations are real and significant, the general point is important. Living organisms can be entrained to environmental rhythms, and the moon provides environmental rhythms that have been present throughout the entire history of life on Earth. The tidal rhythms, the light cycles, the gravitational cycles, all of these are potential zeitgebers, time givers, that biological clocks might be set to. In the moonless world, these lunar zeitgebers would be absent. The biological clocks of living organisms would be entrained to different environmental rhythms: the solar day, the seasons, the annual cycle. They might be just as complex, just as precisely calibrated, but they would be calibrated to different timescales, with different periods, organized around the rhythms that a moonless world actually provides. The effect on human cognition, if humans existed in the moonless world, is genuinely uncertain. The moon's influence on human behavior is real in some respects. The lunar calendar, the tidal influence on coastal cultures, the use of moonlight for nocturnal activity and mythological or marginal in others, the lunar effect on human behavior, for which the scientific evidence is weak. But the deep cultural and cognitive significance of the moon as a timekeeper, a navigator, a subject of mythology, an object of beauty, would certainly be absent in a world that had never had one. The mind that evolved in the moonless world would be a mind shaped by different environmental inputs, different rhythms, different metaphors. It might be a mind just as capable, just as creative, just as curious, but it would have arrived at its capabilities through different experiences and would apply them to different problems in a different world. Agriculture in a moonless world. Human agriculture in our world has deep roots in the lunar calendar. The planting calendars of ancient cultures around the world, from the Mesopotamian farmers who planted by the phases of the moon, to the South Asian farmers who organized their agricultural year around the lunar calendar, to the indigenous peoples of the Americas whose agricultural cycles were intertwined with lunar observations, all reflect the moon's role as a practical organizer of agricultural time. Whether or not planting by lunar phase actually affects crop yields, the evidence is mixed and mostly negative. The use of the lunar calendar as a practical organizational tool for agriculture is universal. The moon provides a natural, easily observable period of approximately 29.5 days that falls between the 2 short day and the 2 long year as a unit of agricultural planning. Planting, harvesting, festivals, storage, trade, all the activities of an agricultural society require coordination across time, and the lunar calendar provides a natural framework for that coordination. In the moonless world, agriculture would still have developed the same basic logic of planting and harvesting applies regardless of the calendar system. But the organizational framework would be different. Without the moon, the intermediate time unit would have to be invented rather than observed. It would be an arbitrary division of the year into smaller chunks, not tied to any obvious astronomical phenomenon. The development of such an arbitrary calendar requires a level of abstract thinking and social coordination that might have taken longer to develop. More fundamentally, the spread of agriculture in our world was facilitated by the stable, predictable climate of the Holocene, the 10,000 years of relative warmth and climate stability following the last ice age, during which the development of farming and the growth of complex societies was possible. In the moonless world, with its chaotically varying axial tilt and its more variable climate, the long periods of climate stability that enabled the agricultural revolution might not have occurred, or they might have occurred at different times, in different places, under different conditions. The agricultural revolution is often cited as the foundational event of human civilization, the transition from nomadic foraging to settled farming that enabled population growth, specialization, cities, writing, and all the other features of complex society. In the moonless world, the agricultural revolution, if it occurred, would have been a different event, occurring in different conditions, producing different crops, organized around different calendars, and leading to a different kind of civilization. The ocean's chemistry without tidal mixing. We have touched on the importance of tidal mixing for ocean productivity and chemistry, but the consequences of the absence of tidal mixing go deeper and further than the simple reduction in nutrient upwelling. The ocean's chemistry is a complex, interacting system, and tidal mixing is one of the threads that holds it together. One of the most important chemical processes in the ocean is the cycling of oxygen. The surface ocean is well oxygenated. The waves and the biological activity of phytoplankton keep the surface water saturated with oxygen. But the deep ocean receives oxygen only through the thermohaline circulation, the sinking of cold, dense, oxygen-rich water at the poles, which flows along the bottom of the ocean and slowly oxygenates the deep. Tidal mixing contributes to the upwelling that returns this deep water to the surface, completing the cycle. Without tidal mixing, the deep ocean would be more poorly oxygenated. The oxygen minimum zones, the layers of water in the middle depths of the ocean, where oxygen concentrations drop to very low levels, would be more extensive. Some regions of the deep ocean might become completely anoxic, devoid of oxygen. These anoxic zones would be hostile to most complex life, supporting only the anaerobic bacteria that can survive in the absence of oxygen. The cycling of phosphorus, the nutrient that most fundamentally limits marine biological productivity, would also be affected. In our world, phosphorus is continuously cycled between the seafloor sediments and the surface ocean through a variety of processes, including biological uptake and sinking of dead organic matter, and tidal mixing that brings deep, phosphorus-rich water toward the surface. Without tidal mixing, the phosphorus cycle would be altered, and the long-term productivity of the surface ocean might be reduced. The calcium carbonate chemistry of the ocean, the chemistry that determines whether calcium carbonate, the material of shells and coral skeletons, dissolves or precipitates, would also be affected. Tidal mixing influences the temperature and pressure conditions in the deep ocean that determine the depth of the calcite compensation depth, below which calcium carbonate dissolves. Without tidal mixing, the calcite compensation depth might be different, affecting the preservation of calcareous shells in the sediment and the long-term carbon cycle. These chemical changes might seem abstract and remote, but they have profound consequences for the biological world. A less productive ocean with larger anoxic zones and a different nutrient cycle would support a different community of organisms. The specific forms of complex life that evolved in the moonless ocean would be shaped by these different chemical conditions in ways that are difficult to predict, but certainly significant. What animals would have lost? Beyond the tidal zone and the oceanic productivity, the animals of the moonless world would have lost something more intimate: the synchronization that the moon provides. Many marine animals reproduce in synchrony with the lunar cycle. The palalo worm of the Pacific, the grunion fish of California, the coral polyps of tropical reefs, all synchronize their reproduction with specific phases of the moon, releasing their eggs and sperm simultaneously to maximize fertilization success. The coral spawning event, one of the most extraordinary biological events on Earth, when millions of coral polyps release their gametes simultaneously on a specific night each year, turning the ocean white with spawn, is timed to the specific phase of the moon with extraordinary precision. Without the moon, these synchronizations would not exist, or rather, they would exist in different forms, triggered by different environmental cues: water temperature, day length, salinity changes, the chemical signals of other individuals. But the precision and the universality of lunar synchronization in marine reproduction is striking, and it suggests that the moon has been a fundamentally important Zeitgeber time giver for the marine biological world for hundreds of millions of years. The loss of lunar synchronization might affect the genetic diversity of marine populations. When many individuals reproduce simultaneously, triggered by the same lunar cue, the chances of genetic mixing are maximized. Many individuals contribute their genes to the next generation in a single event. Without this synchronization, reproduction might be more dispersed in time, with smaller groups of individuals reproducing at different times, potentially leading to smaller, effective population sizes and less genetic diversity. The migratory animals of our world also respond to the moon. Sea turtles emerge from the ocean to lay their eggs on beaches at night, and they prefer to do so during higher tide phases of the moon. The higher tides allow them to nest higher on the beach, above the level of regular wave wash, increasing the survival of the eggs. Without the moon, sea turtles, if they existed in the moonless world, would have to find different nesting cues and nest at different locations. The dung beetles navigate by the Milky Way. The wildebeest time their migrations in part to the lunar cycle. The moths that are attracted to light and are disrupted by artificial light are originally attracted to moonlight as a navigation cue. The entire nocturnal world of our planet is organized in subtle and complex ways around the cycle of the moon. In the moonless world, all of these behaviors would be organized around different cues, different rhythms, different relationships between the organism and its environment. The nocturnal animals of the moonless world might be different in their sensory capabilities. Without moonlight as an available light source, the evolution of vision in nocturnal animals might have proceeded differently. More reliance on echolocation, on infrared sensing, on chemosensory abilities, on the extreme sensitivity to starlight that some nocturnal animals already show. The nocturnal world of the moonless earth might be more dominated by non-visual senses, by sound and smell and touch and magnetic perception, and less by vision than the nocturnal world of our world. The deep sea without lunar forcing. The deep sea of the moonless world would be a strange and different place. In our world, the deep sea is not isolated from the surface world. It is connected by the thermohaline circulation, by the rain of organic matter sinking from the surface, by the internal waves driven by tidal forces, and by the biology of the organisms that perform daily vertical migrations between the surface and the deep. Without tidal forcing, the deep sea would be more isolated. The internal waves, the underwater waves that propagate along the density gradients within the ocean, driven by the interaction of tidal currents with seafloor topography, would be absent or greatly reduced. These internal waves are an important mechanism for mixing the deep ocean and for transporting energy from the surface into the deep. Without them, the deep ocean would be more stratified, more stagnant, less connected to the surface. The biology of the deep sea would be shaped by this isolation. The organisms of the modern deep sea are diverse and extraordinary hydrothermal vent communities, with their chemosynthetic food webs, deep sea fish with bioluminescent lures, cephalopods of enormous size, the vast and largely unexplored communities of the abyssal plain. These organisms are adapted to the specific conditions of the deep sea, the cold, the darkness, the pressure, the low food availability, and their evolution has been shaped by the specific physical and chemical characteristics of the deep ocean. In the moonless world, the deep sea organisms would be adapted to a somewhat different set of conditions: more extreme stratification, lower oxygen levels in some regions, different nutrient concentrations, different temperature gradients. The specific forms they would take are unpredictable, but they would certainly be different from the deep sea fauna of our world. The same general ecological strategies, chemosynthesis at vent communities, filter feeding in the water column, scavenging on the seafloor would be available, but the specific organisms that employed them and the specific ways they employed them would be products of a different evolutionary history in a different ocean. Would intelligence have evolved? This is the deepest question, and the one that most directly confronts us with the implications of the moon's role in the history of life on Earth. We have explored, in various sections of this journey, the ways in which the moon's absence might have affected the origin of life, the evolution of complex multicellular life, the colonization of land, the stability of climate, and the development of agriculture and civilization. Each of these influences, taken individually, might have been overcome. Life is robust and resourceful, and there are many paths to the same destination in evolution, but taken together, they paint a picture of a world in which the conditions for the evolution of intelligence were significantly less favorable than in our world. The factors that contributed to the evolution of intelligence in our world include a stable climate that allowed the long-term accumulation of ecological complexity, the colonization of land, which provided new ecological opportunities and new selection pressures for complex behavior, the evolution of large brains in certain lineages, driven by social complexity and the exploitation of varied environments, and the development of language and culture, which allowed the cumulative buildup of knowledge across generations. In the moonless world, the climate stability that allowed the long-term accumulation of ecological complexity might have been compromised by the chaotically varying axial tilt. Complex ecological communities, built up over millions of years, might have been disrupted by the climate swings associated with large changes in tilt. The deep history of stable environmental conditions that allowed the evolution of complex interdependencies between organisms might have been interrupted repeatedly. The colonization of land, which was facilitated in our world by the tidal zone, might have been delayed or proceeded differently. A world with less terrestrial vegetation or with very different terrestrial fauna might have been a world with fewer ecological opportunities for the specific trajectory that led to intelligence. The evolution of large brains in primate-like ancestors might not have occurred. The primate radiation of our world was made possible by the post-Cretaceous mammalian explosion, which was itself made possible by the asteroid impact. In the moonless world, where the impact presumably still occurs, the asteroid and the moon are unrelated. The same general mammalian radiation might have occurred. But in a world with a different climate history and different ecological structure, the specific evolutionary pathway that led to the large-brained, socially complex primates might not have been available. And even if all these obstacles were overcome, even if life arose, colonized land, evolved complex forms, and produced large-brained, social animals, the absence of the lunar calendar and the lunar navigational tools might have slowed the development of abstract thought and complex civilization in the ways we have explored. The honest answer to the question of whether intelligence would have evolved in the moonless world is probably less likely. Not impossible. Intelligence is a powerful evolutionary strategy, and evolution has produced it multiple times, independently. But the specific conditions that made it easy, or at least possible, in our world would be subtly but importantly different in the moonless world. The probability of the specific outcome, a technological civilization capable of asking the question we are asking, might be much lower. We might not be here. A walk through the moonless night. Let us go outside in the world of tonight and look up, not at the moon. Put the moon aside for the duration of this walk. Look past it. Look at what would be there if the moon were not. The stars. Even with the moon in the sky, even filtered through the light pollution of a modern city, the stars are there. On a clear night, from a suburban garden or a city park, a few dozen bright stars are visible. Orion, perhaps, his belt a neat row of 3. The Pleiades, a small cluster of blue-white points. Sirius, the brightest star in the sky, low in the south. The planets, if any, are visible brighter than the stars, not twinkling because they are close enough to show a disk rather than a point. In the moonless night, the truly dark, truly moonless night of the alternate world, these few dozen stars would become 10,000. The Milky Way would appear, running from horizon to horizon, not a faint suggestion but a real, structured, complex band of light with bright regions and dark rifts, and the occasional smudge of a globular cluster or a nebula. The Andromeda Galaxy would be visible to the naked eye as an elongated patch of light in the northeast, the most distant thing any human eye can see without a telescope, 2.5 million light years away. And the night would be dark in a way that no person living in the modern world has ever experienced. Not frightening, or not more frightening than darkness always is, to the part of the brain that evolved in a world of nocturnal predators, but full, alive. The darkness of the moonless night is not empty. It is dense with information, with the positions of stars, with the movements of planets, with the slow rotation of the celestial sphere that tells any careful observer exactly where they are on the surface of the earth and exactly what time it is. In the moonless world, this is the night that every night would be, not the pale, moon-washed nights of our world's full moon, not the darker, but still moon-modified nights of the crescent or gibbous phases, but this, the unmediated, unlit, magnificent darkness of a world with no moon. Every night, the sound of this night would be different too. In our world, the full moon suppresses the calling of some nocturnal animals. They are more cautious when it is bright, less likely to call and reveal their position to predators. In the moonless world, the night would be consistently dark, consistently safe for the callers, and the nights might be louder, more insects, more frogs, more nocturnal birds calling in the confident darkness. Not a silence, but a fullness. The smell of the moonless night would be the same as the smell of any clear night, the cold, slightly mineral, slightly organic smell of air that has not been warmed since the sunset, the smell of dew forming on vegetation, the smell of the earth releasing the heat it stored during the day. This, at least, would not be different. You stand on the grass, you look up, the stars are magnificent, the Milky Way arches above you, so bright that it casts a faint shadow, the shadow of your hand, barely visible, but there. The universe is present above you in a way that it never quite is when the moon competes for attention. And the absence where the moon should be, the dark gap in the western sky where the crescent or the gibbous or the full disk would normally ride, is not merely an absence. It is a space that the moon has always occupied in our world, since before there was anyone to look at it, a space that, in the world we are imagining, has never been filled. The moon we actually have. We have spent this night imagining the absence of the moon. Now let us spend a moment, before sleep, appreciating its presence. The moon is 384,400 kilometers away. This is close enough that we can see its surface features with the naked eye, the dark Maria, the bright highlands, and close enough that a moderately powerful backyard telescope resolves individual craters the size of cities. It is close enough that the Apollo astronauts reached it in 3 days' travel. It is close enough that it exerts a gravitational influence on the Earth that is felt in every tide, in every coastline, in every organism whose biology is synchronized to the tidal or lunar cycle. The moon is 3,474 kilometers in diameter, about a quarter the diameter of the Earth. This makes it by far the largest moon relative to its planet of any moon in the solar system, except, by some definitions, Charon relative to Pluto. It is not a small satellite, not a captured asteroid, not a faint companion. It is a genuine companion, a second body of planetary scale, co-orbiting the Sun with the Earth, sharing the Earth's fate in its journey through the solar system. The moon's surface is ancient. The dark plains, the Maria, are about 3 billion years old, formed when vast lava flows covered the impact basins of the early solar system. The lighter highlands are older still, perhaps 4.4 billion years old, some of the oldest intact surfaces in the solar system. The craters are records of the bombardment that shaped the inner solar system in its youth, each one a moment of violence frozen in stone, a monument to the chaos from which the peaceful solar system of today emerged. The moon has no atmosphere to speak of. It has no running water, no plate tectonics, no volcanic activity worth mentioning, no magnetic field, no weather. It is, in the ordinary sense, dead, and yet it is more alive in its effects on our world than any other object in the solar system, save the sun itself. It moves our oceans. It holds our axis steady. It lit our nights before we invented fire and before we invented electricity. It organized our time. It gave us our myths. The moon is not optional. It is not a decoration on the night sky. It is a fundamental feature of the Earth system, as fundamental as the oceans, as fundamental as the atmosphere, as fundamental as the magnetic field. Its absence would not merely leave the night darker. It would leave the Earth profoundly, irreversibly different. A faster, wilder, less stable, less productive, less biologically diverse, and possibly unintelligent planet. We are here, thinking about the moon, because the moon exists. This is not a metaphor. It is a statement of probable fact. The specific path of evolution that led to human intelligence was shaped, at every step, by the conditions that the moon helped create: the stable axial tilt, the tidal zone, the organized climate, the lunar calendar, the navigational tools. Without any one of these, the path might have been blocked or diverted. Without all of them together, the probability of intelligence is genuinely uncertain. You exist in part because 4.5 billion years ago, a Mars-sized body struck the young Earth at just the right angle and just the right velocity to produce a debris disk that coalesced into the moon. The moon is a contingency, a product of the chaotic early solar system, not an inevitability. And yet everything that followed from its formation, the tides, the stable tilt, the long nights lit by reflected sunlight, was consequential beyond measure. Epilogue: the light on the water. The moon is rising now, or it will rise, or it has already risen and set. It goes about its ancient business regardless of whether anyone watches it. It rises and sets and waxes and wanes on the same schedule it has kept for 4.5 billion years, indifferent to the remarkable fact of its own existence and utterly unconscious of the life on the planet below that owes it so much. If you can see the moon tonight, if a window admits its light, or if you can imagine it above the roof, riding its slow arc across the sky, let it be the thing you fall asleep thinking about. Not the moon as you have known it all your life, familiar, unremarkable, the background light of night, but the moon as it truly is, a product of ancient violence, a stabilizer of worlds, a lifter of tides, a guardian of an axis that holds the seasons in their place, a light by which your ancestors navigated and planted and told time and made myths. The light on the water tonight, if there is water near you, or if you can imagine water, is the moon's light. It has traveled from the sun, bounced off the ancient, cratered surface of the moon, crossed 384,000 kilometers of space, passed through the atmosphere, and arrived here on the surface of the water in this moment, in this night. It is one of the oldest things in our world. It has been falling on the Earth's oceans for 4.5 billion years, since the moon first formed and the first tide rose and fell in the warm shallows of the young Earth's ocean. The world without the moon is darker and wilder and less stable and possibly lifeless. We will never know it. We live in the world with the moon, the gentler world, the world of tides and seasons and navigable nights, the world shaped by the gravitational embrace of our companion. We live in the world that the moon made possible. Let the light fall. Let the tides turn. Let the axis hold steady in its 23.5-degree tilt, held in place by the moon's quiet, patient, unnoticed gravity. Let the night be lit by something ancient and faithful and far away. The moon is there, and because it is, so are you. Sleep well. Good night.